We're going to move on to our last session, session 4, on satellite imagery and anomaly detection. And David is our first speaker. David Barclay is an associate professor in Oceanography at Dalhousie University and the Canada Research Chair in Ocean Technology Systems, specializing in underwater acoustic technology for applications in naval defense, communication, and marine biology, while utilizing AIS data for passive acoustic oceanography.
Yeah, so we've been using AIS data more and more the last decade. And one of the first things that we're interested in is basically noise modeling, so noise prediction using AIS data. On the flip side, I'll talk a little bit about how we can use AIS data to understand noise measurements. And the other main application is AIS data for tracking. So obviously serving as ground truth with the limitations that it does present. So this is just a figure from, this is a few years of data from the Salish Sea, Strait of Georgia. And these are noise levels at 100 hertz. So noise associated with ship activity. And the kind of interesting thing here was that when COVID happened, there was this drop in sound levels. So that's what kind of got us a little bit excited about this. There's also some other things, sensor drift. Wow, underwater measurements are hard. But anyways, we have this kind of interesting measurement of the reduction of noise from decreased shipping activity. And so this relates back to this idea of trying to come up with predictive models. Here's a really extreme kind of data point to test our models with. But before we, so we're working on that now. We're trying to build a noise model for the Salish Sea. But the interesting thing is you can use AIS data to understand why that drop happened. So here's the AIS data where we just draw a box and just look at the number of unique occurrences happened per week or per day. I don't remember exactly. And you can see, you can start sorting them by class. You see, okay, pleasure craft, that makes sense. That dropped off a cliff because you weren't allowed. The ferry was reduced in the summer. But interestingly, the big one you'd think that would make a big impact, cargo ships actually increased under COVID. So it wasn't a big change there, which was a bit surprising. Oil tankers, there was a big signal, but that was because the oil price crashed because we didn't drive our cars anywhere for a while. So this is just an example of the type of kind of backwards analysis that we can do with AIS data, but we also be doing a lot with forward. We're taking AIS data, trying to make noise maps, comparing them to measurements. On a much smaller scale, looking at tracking sort of on the order of 10 kilometers. So this is just talking about our acoustic methods using a couple pairs of hydrophones. This is looking at kind of fringing patterns at one frequency for acoustic waves. And a colleague of mine calls it an acoustic fingerprint. But basically, no matter how you can draw a line across this fingerprint lots of different ways and get a unique signature. So the idea is we can use these fringing patterns to do localization of ships very effectively. But here's the interesting thing. So we did this experiment using opportunistic ships. Here's the positioning of the ship we tracked, and then the only AIS data we had were these points up there, and there's another point way up there. It comes down to these questions as is the data too sparse to do this kind of localization? How do we start to draw error, error envelope between points, which is something that Mike has told us about a little bit. So yeah, the raw data is important, and thinking about these types of problems that are more on the smaller scale in terms of exact positioning and exact timing are important features that we need to think about when we're trying to serve up the product. And the last slide I want to show, this is from a student of mine who, this is at if you guys know, the ONC, Oceanography Canada, has a hydrophone they stick up in the ocean for the Pacific Ocean and records years and years of data. This is just 1 month of AIS data from near that hydrophone, within 100 kilometers of that hydrophone. And you can see all these beautiful CPAs of ships coming close and going past again. And this is basically in the world of underwater acoustics, using machine learning to track vessels, hot topic, but basically labeled data sets don't exist except for data sets like this. So bringing these large AIS labeled data sets together with acoustic data sets is, I think, something that has a bright future. Anyways, that's all I really want to. 5 minutes or 3 minutes? That's
5. Yeah.
Okay, perfect. So yeah, a couple applications to think about. That's all I really wanted to bring up today.
Thank you very much, David. Yeah, thanks for meeting this time. Yes, thank you. And the next speaker is Seto. May, are you there? Would you want to share your screen?
Here, can you, I'm going to try and share my screen. Can you hear me? You can hear me well?
See you. So May Seto is the Urban Shipbuilding Chief Research Chair in Marine Engineering and Autonomous Systems and an Associate Professor at Dalhousie University. Her expertise lies in autonomy, control of marine robots, underwater acoustics, and robotic navigation. Dr. Seto is currently working on using machine learning and multispectral satellite imagery to combat illegal fishing activities by detecting dark vessels.
Okay, thank you for the invite to participate in this.
Yeah, thank you.
So that's my topic.
Stage is yours.
Can you see my screen? Romina, can you see my screen?
I can see your screen.
Okay, so what I'm trying to do is I'm trying to correlate AIS with satellite-based measurements of ships in the multispectral range to not just detect, but to identify dark vessels as well. So the novel aspects we're looking at is the ability to see through cloud cover. The gold standard for looking through clouds is using radar, so like your radar sats and other large satellites, but the revisit rate is very low, on the order of once every week or so. So the frequency is higher with other methods. So the ability to look through cloud cover could be done through multispectral imagery. Second goal is to assess the feasibility of doing this processing on board the satellite. So in moving your machine learning from the cloud to the edge, the transmitted data volume that you send back to Earth is quite a bit less, and the timeliness of your detections, especially for dark vessel detections, increases orders of magnitude. This is the initial data set that we're working with using a license to look at Sentinel-2 satellite imagery. It's got a multispectral camera with quite a few bands, and what the machine learning aims to do is try to decide which band is most responsive to detection through clouds. So what kind of information is available? From the Sentinel data set, you can get the vessel information if the vessel is actually in the imagery, of course, and every pixel is georeference. What isn't available, which we're interested in, is the cloud type, the terrain type, the ship visibility, and the image suitability. This is an example of how we are extracting data manually for now. So given a certain section, you would focus in on what you think is a detection and then try and correlate it against the information that could be available through AIS. The labeling that we're interested in, so we want to be able to detect different levels of cloud, smog, light cloud, heavy cloud, right? And so visually you can't always see through it. And again, of the 13 multispectral bands that we look at on the camera that we access, there are 3 bands that look promising, and the machine learning is what we're trying to apply to decide which bands. The next data set we want to do is based on a satellite we're hoping to build. So Dalhousie University's LoRa satellite was successfully built, launched in December 2022. We recently secured funding to build a 3U satellite, this one with a multispectral camera payload. So what we're interested in collecting is the ship imagery through a variety of different cloud conditions, and also imagery on trees and vegetation towards climate change measures. So the questions for the wider community, for anyone who wants to work with us, we find that the AIS measurements do not always correlate well with what the in-orbit imagery suggests. Sometimes we would have an AIS detection that's supposed to be in the image, and we cannot see the vessel at all. As well, beyond ports and harbors, we're interested in open water detection and identification. That's where it is the most useful. So our project looks at a much later stage where you've got potential ships available and you've got the AIS data available. So efficient methods to detect ships based on their displacement, if possible. And as well, we would welcome discussion with anyone who wants to contribute to our project or are interested in the data. That's all I've got. Thank you.
Thank you very much, May. And we will have questions after our last talk, which is our last Zahra Sadeghi. Zahra is currently a postdoc fellow at Dalhousie University's Institute for Big Data Analytics. Her research focuses on utilizing machine learning models and AIS data to improve situational awareness, security, and safety during open water navigation. Specifically, she works on detecting anomalies in the maritime domain.
So I'm going to talk about maritime anomaly detection today. So first, let's talk about the motivation and importance of this problem. So maritime anomaly detection is very important. It's essential for ensuring the safety and security of navigation across the ocean, and it's also important and critical for maritime transportation protection. So by identifying the species activities, we can avoid and prevent dangerous situations such as collision, illegal activities, or illegal fishing, smuggling, such as drug and weapon smuggling, pollution, and piracy. So in order to identify the anomalous points, you need to do time series analysis on AIS dataset. And by the end of this workshop, I think all of you should know that AIS is an automated tracking and monitoring system. So it's facilitated by continuous transmission between nearby vessels as well as the AIS base stations and satellite. And when we talk about time series of AIS dataset, we mean the sequential data that comes from the AIS messages that are sent between different vessels. So studying these time series can help us to extract different behavior and features from the movement of vessels across the ocean. So in the bottom of the slide, you can see some examples from the latitude attribute of time series data for AIS dataset. So now what's anomaly and what is outlier detection? So anomaly detection mainly refers to dealing with identifying unlikely and rare events. So we mainly want to find the observations that do not fit with the typical and normal statistical distribution of the data set. So the main objective here is to classify the data into two groups of normal and abnormal or anomalous. So normal data are a sign of situation which is safe and legal, whereas the anomalous data are corresponding to situations which are dangerous and illegal. Also on the bottom side of the slide, you can see a figure that shows how anomalous points look like in a time series data. But this problem is very challenging, and part of the challenge, or maybe mostly the part of the challenge, is about the AIS dataset itself, because AIS dataset is inherently unreliable, noisy, and inaccurate. And one reason for that is AIS messages are entered by operators, and so they have to be put by hand. So this is like a manual process, and so it's error prone and can be very noisy. Also, sometimes we can see that there are large line gaps between different messages. That's because if the operators don't update the information on a timely manner, we can see and we can observe these line gaps. Also, the other problem is that AIS signals can be easily spoofed by attackers who wish to obscure their location, and they want to falsify their locations if they want to do some illegal actions. And the next problem is due to the fact that there is no well-known anomalous AIS data set. So this is about a lack of annotated public data set. And why we don't have a public data set? This is because labeling sequence of data actually for the AIS data set is a very time-consuming and expensive manual task. So we can suppose that each of the trajectories can contain thousands of data points, and labeling each of these data points manually is very time-consuming and expensive, and there are abundance of unknown and unidentified anomalous events, and we really need domain knowledge in order to identify each of these events. And so we don't have a well-studied anomalous AIS situations, and there is no reliable ground truth. But however, common ML approaches require training models on an annotated data set in order to be able to make a distinction between anomalous and non-anomalous points. Here are a couple of well-known anomalous AIS behavior. The first one from the left is a situation when there is a deviation from a standard route. So the curve in orange shows you an anomalous behavior, and as you can see, one vessel is deviating from the standard route, which is and it's showing an anomalous behavior. The second one from the left is known as unexpected activity. So this is referred to the case when we can see a curvature from the data which doesn't make sense. For example, in this example, we see that some data points are coming from a different location, and there is this non-continuity curve which is not expected. And the third one is unexpected port arrival. So for each vessel, we have some estimation about the arrival time, and if the arrival time doesn't match with the one that is expected, this is another flag that shows that something is wrong. And the fourth one is close approach. This happens when one vessel doesn't keep the standard distance from another vessel, and there is a close proximity between two vessels. And the last one is known as zone entry. This happens when one vessel enters one area that is a restricted zone, or this is when the information is coming from a zone which is supposed to be a land area. Okay, so because I'm a last speaker, I think I can talk.
We'll have some questions too.
Yeah, so I'm just going to briefly mention some of the ML techniques for anomaly detection. So broadly speaking, we can divide the ML techniques into three groups of supervised, semi-supervised, and unsupervised, and they are different based on the amount of label data that are required. The supervised method is the one that really needs full amount of label data. The semi-supervised tries to alleviate this problem and requires less amount of label data, and the unsupervised approach is where we don't need any label data at all. And I'm also going to go into more details about some of the other ML techniques for anomaly detection. The first one is prediction-based methods, and the methods from this family try to model the behavior of data using autoregression models such as ARIMAS, SARIMAS, SARIMAX, ARMA. So there are many different range of this family. The advantage of this approach is that it doesn't require any label data, but it's very sensitive to parameter selection and can show poor performance for long trajectories. And the figure can also show that when there is a high error between the predicted pattern and the actual pattern, we can flag it as an anomalous point. The next approach are called clustering-based methods. These are kind of a very simple idea in machine learning that we try to group data based on the similarity or distance measure. And the advantage of this approach is that they can be applied in an unsupervised way, but the disadvantage is that we require hyperparameter tuning, and it's not really optimized for finding anomalies. Finding anomaly is a byproduct task in these methods. And the last one, my last slide, is the methods which can be called network-based methods. And by network-based, I mean the deep learning methods. So traditional methods that I have mentioned so far are not very really capable of finding efficient answers due to the unpredictability and complexity of maritime navigation. So deep learning methods can be applied into flavor of supervised and unsupervised. Some of the well-known approaches are the sequential modeling, like RNN, LSTM, AE, GNU, and so on. The advantage of applying deep neural network is that they can learn high-level and complex features automatically, so we don't require any feature engineering, and they have the capability of self-learning. And they are also having high performance, efficient, and accurate. They are very accurate, but the disadvantage is that these modeling require large amount of data, and they are computationally expensive. So I try to go very quickly. Thank you so much. So if you have any questions, I will be glad to take them.
Thank you, Zahra. Yeah, we'll ask David and Zahra to come to the front, please, and then may join with the camera on, please. And then we'll take questions from the audience. Are you still there? Yeah.
I am.
So you showed like a couple of graphs, but some of them showing that there was a decrease in passenger vessels and oil tankers, but an increase in cargo vessels. But even so, there was a massive dip in the noise levels. So would it be fair to say as well that the passenger vessels and perhaps the oil tankers contribute way more to the noise levels than?
Yeah, I think one of the things is, again, how you process the data. So that was, we just took unique hits per day. And the ferry, which goes back and forth, Victoria, Vancouver, I think that it didn't ramp up at the seasonal level probably was the greatest contributor to that. So again, kind of the importance of twisting the AIS data the right way. Yeah.
Thank you.
Scott?
Yeah, I have a question for May and this multispectral data. So you mentioned that you want to try to figure out how to classify these clouds in some kind of way. Is that because you're trying to determine how successful multispectral can be through different thicknesses of clouds, or is it trying to exclude heavy clouds while trying to be able to identify things through thinner cloud covers? What's going on there?
So if with multispectral, you're going over a range of frequencies or wavelengths, some of them can penetrate waters, so like clouds, better than others. So of the 13 bands, we want the model to learn which bands or fusion of bands gives you the best results for looking through the clouds. So that's the machine learning aspect to determine which cloud cover is something we're going to penetrate well with the multispectral bands that we have and which will not. I don't know if that answered your question.
It does. So it's more so just depending on whether you identify the cloud, you'll be using a different band combination to look for the vessel.
Yeah, well, to first penetrate the cloud and then to look for vessels.
Thank you. We have a question from Lee.
Yeah, I've got a couple questions actually, one for May and one for Zahra. May, I was curious, in one of your slides you had showed that you're detecting vessels which sometimes don't correspond with the AIS data, which makes sense if you're trying to look for dark vessels, so they may not be transmitting or they may be spoofing their transmissions. I'd seen a paper on a similar topic where they're kind of looking at the same thing and trying to identify if a vessel is not transmitting. They try to extrapolate the kind of trajectory of the vessel during the time it's not transmitting and then see if they can identify what the vessel was, kind of which AIS transmission would have corresponded to the detection that they made. So I was wondering,
speaking more of vessels that have their AIS turned on. Right, so that's the ground truthing. The AIS is turned on and the multispectral camera hasn't captured it. In where it said it would be. So obviously, yes, if they didn't have their AIS on, then that'll create problems. But for that paper, do you have a name or
yeah, I can grab it and put it in the Teams chat in a sec.
Okay, that'd be cool. Thank you.
Yeah, it's just kind of curious if you're trying to do that type of mapping. So if a vessel does not have an AIS transmission turned off, are you trying to figure out what the vessel identifier might have been before it turned it on? Or is your focus really just on dealing with the kind of penetration of clouds and picking out vessels first of all?
Well, it's both. So we want to show that it's efficacious to use multispectral on satellites, and that it's a lot less cheaper than and easier and faster than relying on other methods. And secondly, once we've penetrated the clouds, because we also have lots of data where there's no cloud cover, can we do a differencing to determine that a vessel might not have its AIS on, but we clearly see it.
Yeah. Okay, interesting.
Yeah.
Thank you.
Yeah, send me that paper. Thank you.
Yeah, will do. And question for Sarah. So you had mentioned quite a few different methods that can be used for anomaly detection within vessel movement. I was wondering, have you done experiments with those different methods to compare them, or do you have plans to run experiments, or is this just kind of a survey for the time being?
Yeah, so for the purpose of this workshop, I figured to give you a survey, but my current work, so I've been working on different ways of modeling the AIS dataset in order to detect anomalous data points. One of the methods that I applied was based on autoencoder. So in that experiment, we had to train an autoencoder and then do different analysis based on the density of the movement of the behavior of the vessels that have been trained with that autoencoder. But I have also applied different types of clustering, and also another method which is based on autoregression, and trying to model and predict the behavior of the data using autoregression model. Specifically in my case, I use ARIMA modeling. And so then the third, I can say, modeling that I applied was based on it was kind of a statistical approach in order to extract meaningful information that shows how the behavior of trajectories can be kind of changed, and how we can how we can drive a modeling that can find the spikes in the trajectories of data. That was mostly based on ideas from statistical analysis, which was combined with kind of image processing. So I didn't mention these approaches. So because of 5 minutes, I tried to just give you a review about the existing models.
And based on what you've looked at, do you have any conclusions about which models seem the most promising? I would sort of think that the autoencoders might be a good one, but did you find other ones look more reliable than those?
Yeah, so based on my experimentation, I would say that applying sequential modelings, and especially autoencoders, are very beneficial, so they can efficiently learn the behavior of modeling. I'm also working on another type of modeling based on VAE, which is another version of autoencoder. It's called variational autoencoder. It can give a better representation of data, so the hidden layer that we can obtain with VAE is more advanced than autoencoders. Autoencoder is kind of a vanilla type of sequential modeling. So I've been working on this VAE because I saw that they can very much efficiently learn the complex behavior. So for example, with ARIMAs, like other types of autoregression models, we always have this limitation that they can't learn the data when it's consisting of a line trajectory. They just they don't give good performance for line trajectories, and there are many missing information there. But with deep neural network, because of this feature that we can segment the data and then feed these sequential models segment by segment, it gives us this capability to find to model the data much better. And also the other advantage of these techniques is that they can, so like when we try to learn the behavior of one vessel type, we have like thousands of trajectories of data from that vessel type, and deep neural networks can really learn very effectively when we have large amount of data, because so like these are very much data-driven approaches, and if you have a good amount of data, high amount of data, then the modeling the model that they can learn is very much fitted to the data, and so the performance that we can get with the deep neural networks are comparatively better than the traditional approaches. And also, you know, we can also do many other experimentations. For example, by analyzing the latent and latent space and the embedding that we obtain, we can also find many information. We can see a lot of discover. We can discover a lot of different features that occurred between different models. So between different models of different vessel types. So for example, we can have autoencoder, which is trained on, for example, cargo, and then by just analyzing the latent space between the model that's been trained on cargo and the one that's trained on tanker, we can find the differences in representation space. So I don't know, so these are like kind of technical questions, so I would be glad to go into more details. I hope that I at least could have answered part of your question.
No, absolutely. That covers it very well. Thank you. And definitely interested to see any further results that come out of that line of investigation. Thanks.
Sure, thank you.
Thank you. We have a question from Norma.
Yeah. Hello, I hope you can hear me okay.
We hear you. You're really very quiet.
Oh, okay. I'll try to speak up then. I'm with Transport Canada, and I have a question for Mai. So I'm interested in actually vessels that not necessarily transmit AIS because they're not required. So wondering what's the minimum size of vessel you can observe with the multispectral if you're looking at that. And then if there's any difference in terms of the materials that the vessel, like if it's a wooden vessel versus, you know, other materials that are made out, if that makes a difference in the detection.
I'll address your question first about minimum size. So that's usually quantified based on the displacement of the marine vessel. But if you prefer looking at it from a displacement point of view, 20 meters, minimum 10 meters. Smaller vessels than that, then we're going to have to come really close into Earth to see it from low Earth orbit. And as far as the perception of the vessel based on its materials, that again depends on what band you're viewing it with. Wooden vessels and metal vessels, I have not seen. There may be a difference. If there is, I'm not aware of it, because most of the vessels we've looked at are mainly larger metal, you know, aluminum or other hollow forms. Yeah, I mean, some materials be more responsive over some bands than others. But I don't personally know of a strong difference between, say, wood and metal. Right, it's almost like visual. When you're looking in the visible wavelength, it doesn't matter as much. I guess it depends on the ambient and everything. Right, it's just now you're seeing further out beyond the visible wavelengths. I don't know if I answered your question.
Yes, yeah, I believe you did. So thank you so much.
You're welcome.